Hello there, and welcome to Just About Earth, the corner of the internet where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're going to drift into a question that's as old as the oceans and as big as the sky, but it's one you might have never really thought to ask. It's a question that's been hiding in plain sight, lapping at our shores and swirling in our teacups. Where did all the water on Earth come from? It's a funny thing, isn't it? Our planet, this famous pale blue dot, is just awash with water. We have oceans that cradle entire continents, clouds that whisper across the sky, and rivers that braid their way through the land like silver threads. Water is so ordinary, so fundamental to our lives, that we sometimes forget just how extraordinary it really is. The seas feel like they've been here forever, but they had a beginning. And that beginning, well, it might be a lot older, colder, and stranger than you imagine. So before we dive into cosmic clouds and ancient stones, let me just ask, what time is it where you are right now? Are you starting your day with a morning coffee, enjoying a quiet afternoon, or settling into the hush of midnight rain? Wherever you are, I hope you find this journey soothing. If it brings a little bit of wonder to your wind down, I'd be so grateful if you'd consider liking the video, subscribing, or maybe sharing it with someone else who's also floating through time and curiosity. Alright, find a comfortable spot, let your thoughts begin to slow, and let's begin. Because in the story of our Earth, water is both the ink and the paper. And to find its source, we have to sail beyond the sky, across time itself, to a moment before there was even a sea to remember, a fireball with a secret. Roughly 4.6 billion years ago, the Earth was born. But it wasn't the gentle blue marble we know today. It was a fireball dry, molten and merciless. And yet, here we are, on a world where over 70% of the surface is covered in liquid water. That's a delicate, rare, and life-giving phenomenon. So how did it get here? Was it always part of Earth's makeup, just lurking deep within its molten heart? Or did it come from somewhere else, delivered perhaps by icy messengers from the depths of space? Tonight, we're going to follow the water's story. From interstellar ice to secrets hidden in the deep mantle, from violent cosmic impacts to the first gentle rains. Because to understand where Earth's water came from, we have to go back, way back before there were oceans, before rivers, before Earth even had a solid surface. We have to go back to the very beginning. It's amazing how a huge discovery can start in a quiet, unassuming place. Deep in the quiet vaults beneath Honolulu, inside a building that could easily pass for just another university annex, a tiny fragment of Earth's deep memory once kicked off a cascade of questions that reached all the way out to the stars. The year was 2014, and a team of geochemists, led by Dr. Lydia Hallis, was studying these microscopic inclusions inside an ancient basalt rock. Think of this rock as a relic from the early mantle of the Earth, brought up to the surface by volcanic forces millions of years ago. These inclusions were just tiny specks of glass trapped inside a mineral called olivine, but they were carrying isotopic fingerprints clues, whispers from a time when our planet was still forming. And inside those clues, they found something strange. They found a specific type of hydrogen called deuterium, or heavy hydrogen. The ratio of this heavy hydrogen to regular hydrogen, what scientists call the D-H ratio, is a kind of cosmic signature. You see, different sources of water throughout the universe have different D-H ratios. And what Dr. Hallis's team found was this. The D-H ratio in those samples from the deep mantle was much lower than the ratio we find in our oceans today. It was also much lower than the signature carried by most comets. In fact, it closely matched the D-H ratios found in certain types of meteorites, specifically a group known as carbonaceous chondrites, primitive, ancient space rocks. This tiny chemical difference cracked open a window to the past and poured starlight right through it. In that moment, they realized something extraordinary. Earth's water may not have come from comets, as had been assumed for a very long time. It might have come from something even older, from the very building blocks of the planet itself. To make sense of that, we first have to understand how the Earth was formed. It wasn't a quiet miracle, it was a storm of stone. The solar system was born in absolute chaos. A rotating disk of gas and dust, called the solar nebula, surrounded the young sun. It was hot, turbulent, and glowing. Within this disk, tiny grains of dust started to stick together. Then they clumped up, Then they collided. Over millions of years, they formed larger and larger bodies, planetesimals, then protoplanets. It was a cosmic demolition derby, where gravity was both the hammer and the glue. Our Earth began as one of these protoplanets, a growing ball of rock and metal being smashed together from countless smaller pieces, and some of those pieces carried water. But not the way we think of water now, not as oceans or rainstorms. This was water trapped inside minerals, bound tightly within the crystal structures of silicates, hidden away in dust. These were hydrated minerals that had formed in the cold outer regions of the solar nebula, far from the sun's warmth. They journeyed inward, carried by migrating asteroids and nudged by gravity. When they collided with the growing Earth, they released their ancient moisture, not in gentle drops but in violent bursts of steam. And that's the paradox. Earth began hot, really hot, hot enough to vaporize anything wet that came near it. The surface was a molten magma ocean. The atmosphere, if you could even call it that, was more of a temporary blanket of rock vapor. So, how did any water survive this inferno? Well, a lot of it didn't. Much of the water delivered early on was likely lost, boiled off into space by the intense solar wind, or blasted away by giant impacts. But not all of it. Deep beneath the surface, some of that water found refuge. It stayed locked into those minerals, sinking slowly into Earth's forming mantle. And as the magma oceans finally began to cool and the crust started to form, a process called volcanic outgassing began. Steam, hydrogen, oxygen, carbon dioxide all came pouring out, and among them was water vapor. For the first time, rain began to fall. Not a gentle drizzle, but torrential storms that must have lasted for thousands and thousands of years. Rain that literally turned fire into ocean. So if Earth's water came from these ancient water-bearing planetesimals, these chondrites, then maybe Earth was always destined to be wet. Maybe not blue at first, but damp, deep down inside. Which raises a beautiful possibility. The ingredients for our oceans were baked into the recipe from the very start. Still, the picture isn't quite complete. Because even if the ingredients for oceans were baked into the recipe from the very start, there's another piece of the puzzle we have to look at. A piece that for a long time was considered the main suspect. I'm talking about those icy comets that blaze across our skies like whispers from the outer dark. Messengers from the cold. For decades, comets were the prime suspects in the mystery of Earth's water. And honestly, you can see why. After all, they're made largely of ice. What could be more intuitive? These icy visitors from the Kuiper Belt or the distant Oort cloud would come screaming into the inner solar system, slam into the early Earth and melt, filling up our seas. It's a simple, elegant idea. And indeed, early in Earth's history, impacts were incredibly frequent, violent, and were literally shaping the planet. There was a period around 4 billion years ago known as the Late Heavy Bombardment. It was a time of relentless cosmic rain, not of water but of rock and ice. If comets were responsible for delivering Earth's water, that would have been their moment to shine. But, as we've already seen, when we actually measured their isotopic fingerprints, their D/H ratios, something didn't quite match up. Most of the comets we've studied have too much deuterium. Their water isn't the same as Earth's water. It's close, but it's not quite right. It's like finding a puzzle piece that's almost the right shape, but no matter how you turn it, it just won't click into place. Now, to be fair, some comets, especially those that seem to come from the asteroid belt rather than the distant outer solar system, do have D/H ratios that are closer to Earth's. But even then, the match isn't perfect. And more importantly, when you do the math, the amount of water they could have delivered just isn't enough to fill our oceans. So, perhaps comets played a role, but it was likely a minor one, more of a cosmic drizzle rather than a planet-soaking flood. It's those carbonaceous chondrites, those ancient water-bearing meteorites, that still seem to carry the best chemical match. They formed in the early solar system, they wandered through space, they collided with our growing world, and in doing so, they now seem to be the most likely couriers of Earth's oceans. And yet, this story, as rich as it is with isotopes and orbital mechanics, still leaves so much room for wonder. Because even if the water was delivered by space rocks, the moment it rained down upon this world, it transformed everything. I want you to try and imagine it. Picture a red-hot Earth, its fresh crust cracking with magma flows, the sky thick with steam and volcanic gases, and then the first true storm. Not lightning and thunder, just rain. Unending sheets of it, falling for centuries, maybe even millennia. Rain that was hot, maybe even boiling at first, hissing as it struck the molten rock. It sculpted the first primitive river channels and began to fill the first basins, birthing the very first sea. Water, born of stone and fire, was beginning to drape the planet in life's future promise. So the next time you dip your fingers into the sea, or feel the rain on your face, remember this. You're touching a molecule that once rode through the dark of space, bound to a pebble older than the Earth itself. It crossed billions of miles. It endured the violence of impact, the searing heat of a molten world, and immense pressure. And somehow, it remained, ready to become part of an ocean, part of a cloud, a tear, a single breath. Water didn't just come to Earth, it stayed, the Hadean world. Before the seas churned, before clouds even had the breath to form, Earth was a smouldering, spinning question mark suspended in the newborn solar system. I want you to really try and picture it, not the lush blue marble we know, but a tempest of stone and heat, a molten sphere glowing faintly red, like the eye of a forgotten forge. Its surface wasn't solid, not yet. It was a restless ocean of lava, constantly stirred by impacts, constantly reshaped by the chaos of its own birth. This was Earth in its first few million years. And in this version of our planet, water, if it existed at all, was not something you could drink or swim in. It was a ghost, a vapor, a chemical whisper bound inside rocks or drifting like steam through an atmosphere thick with sulfur, carbon dioxide, and silicate vapor. Back then, the atmosphere was not the gentle blue envelope we breathe today. It was choking and dense, more like a plume from a volcano than a sky. Volcanic outgassing pumped it full of greenhouse gases, while the sun, much fainter than it is now, cast a pale, weak light across a world that still had no oceans to catch it. There were no continents, no stable crusts to stand on. Any land, where it existed, was fleeting, hardened temporarily by cooling, but often broken apart again by new flows of magma. And in this shifting seascape of fire, deep beneath the forming crust, minerals were beginning to capture hydrogen and oxygen. They were holding the raw ingredients of water in silicate cages that would eventually be unlocked by heat and pressure. This early world was governed by processes we can barely even imagine today. Giant impacts were common. Some were so massive they could melt entire hemispheres of the planet. One of these impacts, perhaps the most famous of all, is thought to have formed our moon. A Mars-sized body, which we've named Theia, is believed to have collided with the proto-Earth, ejecting enough debris into orbit to form a satellite and completely reshaping our young planet forever. And yet these cataclysms were not the end. They were part of the beginning. Each impact, each fracture in the crust, offered new pathways for internal gases to escape. Hydrogen, carbon monoxide, and of course, water vapor. As the planet slowly cooled, these gases began to condense. What once boiled skyward began to fall back down. The first rains, likely acidic and utterly alien, began their descent. Imagine the sound. Not a gentle pitter-patter, but a constant, roaring hiss as rain struck magma, exploding instantly back into steam. Rivers couldn't form yet. There was no land stable enough to carve. Instead, pools of water probably boiled away as quickly as they appeared. But slowly, steadily, the surface began to change. The cooling took time, hundreds of millions of years, but eventually the magma oceans gave way to a solid crust, as thin and precarious as it was. It cracked and buckled under its own heat, releasing more gas, more steam, and giving water more of an opportunity to linger. This was the Hadean Aeon, named for Hades, the underworld, and it was a fitting title for a place of such unimaginable fury and fire. But even in this inferno, the requirements for life's eventual arrival were quietly being assembled. And here, we have to pause. Because to talk about water on Earth, without talking about what's going on deep inside the Earth, is to skip the very heart of the story. Miles beneath your feet, far below the crust we live on, lies a region called the mantle. It's solid rock, but it's so hot that it flows like incredibly thick tar over millions of years. It's in this mantle that Earth stores its most ancient secrets, and astonishingly, we now believe that the mantle holds as much water as, or perhaps even more than, all of the oceans on the surface combined. Now, this isn't in the form of giant underground lakes or hidden rivers, This water is locked inside the molecular structure of minerals like ringwoodite and wadleyite. These are special crystals that are only stable under the immense pressures found deep within the earth, and they are capable of trapping water within their very structure. This water doesn't slosh or drip, but it's there. And it tells us something absolutely remarkable. Earth didn't just get water delivered from the outside. It may have actually grown up wet from the inside out. Because those planetesimals, the chondrites and other early space rocks, didn't just bring water to the surface. They brought it deep into the planet's core components, into the very bones of the world. And some of that water never left. The implications of this are staggering. It means water wasn't a latecomer to the party. It was foundational. It was present during differentiation, when Earth's heavy iron core sank and the lighter silicate layers rose to form the mantle. It was present during the giant, moon-forming impact. It was present perhaps when the first seas finally gathered in basins that were cool enough to hold them. The first seas and a hazy sky. Let's turn back to those seas. Once the surface finally cooled enough to remain solid, and the atmosphere had thickened with enough vapor, Earth's first true oceans began to appear. This didn't happen all at once. There was no single, sudden moment when someone could have looked out and seen a gleaming blue expanse. But over a vast stretch of time, puddles became lakes. Lakes joined together to form seas, and eventually, the oceans formed. They were likely shallow by modern standards, and they were constantly being reshaped by volcanism, meteor strikes, and the first tectonic rumblings. The skies above these new oceans were not yet blue. With no free oxygen in the atmosphere, the sky was probably a hazy orangish soup of methane, ammonia, and carbon dioxide. The sun's powerful ultraviolet rays pierced right through it, and without an ozone layer to protect the surface, deadly radiation bathed the planet. And yet, despite all of this, the oceans endured. They were held in place not by gravity alone, but by Earth's unique and delicate balance of heat, pressure, and atmospheric conditions. It was a perfect recipe. Just a little bit closer to the sun, and all the water might have boiled away forever. A little farther out, and it might have frozen solid. But here, in this perfect range we now call the habitable zone, it lingered. Still, these early oceans were nothing like the ones we know. They were acidic. They were probably a murky, greenish color from all the dissolved iron. And they were warm, constantly stirred by geothermal activity from below. All across the ocean floor, hydrothermal vents, think of them as underwater geysers, fed by volcanic heat-spewed minerals and heat into the depths. These vents formed incredible, dynamic environments that many scientists now believe could have been the cradle of life itself. There were no coral reefs, no fish, just water, rock, heat, and time. And perhaps something else. Organic molecules, drifting in from space on meteorites or forming in the chemical broth of the early Earth. Amino acids, simple sugars, the very seeds of biology. In these ancient waters, chemistry had all the room it needed to stretch out, to experiment, to combine and recombine. And perhaps, quietly, slowly, to awaken. Because before Earth became a home, before it was lush and green and full of voices, it was simply wet. A planet of storms, of seas, and of silence. And in that silence, something was beginning to stir, written in the ratios. To understand the true source of Earth's water, not just how it arrived, but how it managed to take root, stay, and reshape the very nature of our planet, we have to follow a trail that's written not in oceans, but in isotopes. It all begins with hydrogen, the most abundant element in the universe. It's light, it's ancient, and it was forged in the very first moments after the Big Bang. But not all hydrogen is the same. Some of its atoms carry an extra neutron, which makes them a little bit heavier. This variant is called deuterium. It's still hydrogen, just with a bit more heft. The ratio between regular hydrogen and this heavy deuterium acts like a cosmic passport stamp. It can tell us where a given sample of water has been, whether it condensed in the cold, outer reaches of the solar system, formed on a chilly asteroid, or emerged from volcanic gas. This is the D-H ratio. Earth's seawater has a very specific D-H ratio, and for decades, scientists have been comparing it to every known source they can find. Icy comets, asteroids, meteorites, and even the solar wind. The results weren't just data points, they were fingerprints, and they pointed to something strange. Let's start with comets. Those icy nomads from the solar system's fringes seemed like the perfect water couriers. But as we've discussed, most of the ones we've studied, like Halley's Comet or Hale-Bopp, have D-H ratios that are significantly higher than Earth's. If our oceans came from these icy wanderers, they would be chemically different. They are not. It's a lovely idea oceans delivered as cometary gifts, but the math and the chemistry just don't add up. That brings us back to meteorites, specifically that rare group called carbonaceous chondrites. These are among the oldest solid objects in the solar system, tiny time capsules that formed in the dusty midplane of the solar nebula over 4.5 billion years ago. Many of them never underwent the melting and reshaping that larger bodies did. As such, they preserve their ancient chemistry, including their water. And when researchers began studying their D-H ratios, a clear pattern emerged. They matched Earth's oceans not just closely but almost perfectly. These meteorites contain hydrated minerals, proof that water wasn't just carried on them, but was locked inside their very structure. And their isotopic fingerprints suggest they formed in a part of the solar system not too far from where Earth itself was assembling the inner asteroid belt. Suddenly, a much clearer picture started to form. Earth didn't have to wait for comets to bring it water. It inherited it, not as ice, but as hydrated rock. A delivery made not in giant buckets, but in billions upon billions of tiny grains. This process likely began during accretion, the period when the planet was growing by sweeping up material in its orbit. As the proto-Earth gobbled up rocky material, some of it was dry, but some of it was wet. These wet bits contained silicates rich in OH bonds essentially, water that was chemically bound into the minerals themselves. This wasn't surface water. This was deep water, trapped in the very fabric of the forming mantle. And when the planet began to differentiate, when heavy elements like iron sank inward to form the core and lighter silicates, rose to create the mantle, those hydrated minerals were carried along for the ride. But this wasn't just a matter of storage. It was a process of transformation. Over time, as internal heat built up from radioactive decay and the pressure of its own mass, these bound waters were squeezed out and released. The Earth began to outgas. It wasn't just exhaling carbon dioxide or nitrogen, it was exhaling water vapor. Plumes of steam rose from massive fissures in the young crust and flowed from the first mid-ocean ridges. The planet was breathing out, and its hot, volatile atmosphere became saturated. Eventually, when the surface had cooled just enough, that water vapor condensed. The rains began, and they did not stop. It wasn't a single storm. It was an epic of deluge, a hydrological era where clouds formed endlessly and rain pounded the barren surface like a baptism. Pools merged into seas, and basins filled. Water collected in the lowlands, carving the first paths, shaping the first valleys, even as the crust itself was still shifting and buckling beneath. Colder, stranger, older. But there's another theory, one that's even older, colder, and stranger. Some scientists propose that Earth's water began arriving even before the planet itself was fully formed, carried in on the very dust from which it grew. In the frigid, distant reaches of the solar nebula, well beyond the young sun's warmth, ices formed not just of water, but of carbon monoxide, methane, and ammonia. These ices coated tiny grains of silicate dust, the raw material of planets. As turbulence and gravity stirred this massive disk, some of these icy dust grains began to drift inward. They didn't melt right away. Instead, they stuck to the growing clumps of matter. They added their mass to the forming planetesimals, and they brought their water with them. In this model, Earth's wetness isn't an add-on feature. It's primordial. The planet didn't become wet. It was born wet, at least in its constituent parts. This idea might explain something very curious: the remarkable consistency of water's isotopic signature across the entire planet. From rocks deep in the mantle to the surface oceans, from the polar ice caps to underground aquifers, the D-H ratio remains incredibly stable. That kind of uniformity suggests a single, shared origin, not a patchwork of different deliveries from various comets and asteroids, but a foundational source that was well mixed from the very beginning. But there's still the crucial question of retention. Even if water arrived early, how did it manage to stay? The early Earth was hot, brutally hot, hot enough to boil water instantly and strip light gases from the atmosphere. Some researchers believe Earth's first oceans may have formed and then vanished, lost to space, boiled away by the solar wind, or blasted off by massive impacts. So why didn't all the water escape? There are likely two main reasons. First, Earth is big. Its gravity is strong enough to hold on to heavier molecules like water vapor, even during the most violent periods of its youth. Second, by the time water was truly abundant on the surface, Earth had begun to form a magnetosphere. This is a protective magnetic shield generated by the spinning of its molten iron core. This shield acts like a cosmic force field, deflecting the harsh solar wind and preserving our atmosphere and all the water within it. Without this magnetosphere, Earth might have suffered the same fate as Mars, a planet that we know once had liquid water, but lost most of it to space over billions of years. So, the real miracle isn't just that Earth received water, it's that it managed to hold on to it, that it kept raining long enough, that it cooled quickly enough, and that it protected itself fiercely enough to cradle the oceans we know and love today. Water came early. It came often. But most of all, it stayed. And in that simple act of staying, everything changed. The deep water cycle. Let's return now to the Earth, not as a molten sphere or a newly crusted orb, but as a world at a threshold, a place just beginning to wear its oceans like a loose-fitting robe. Something profound was shifting not in a single moment, but across millions of years, as water moved from being a vaporized dream into a permanent planetary feature. The transformation was not subtle. It involved the entire planet's geochemistry, the deep cycles of heat and pressure that dictated whether water remained locked in minerals or burst free in plumes of steam. This is where Earth's deep mantle re-enters the story, not as a background detail but as a central player. You see, the water cycle we all know, the endless rise and fall of evaporation, condensation, and precipitation, isn't just a surface phenomenon. There's another, much slower cycle that happens deep beneath our feet, one that may be just as old and just as vital, the deep water cycle. It works like this. As tectonic plates move, grinding against each other, sinking and colliding, some are forced downward into the mantle in a process called subduction. And as they sink, they drag seawater with them, not as liquid, but bound within hydrated minerals like serpentine. This water travels deep into the Earth, sometimes hundreds of kilometers down, where immense pressures and temperatures squeeze and bake it into new forms. Some of it stays trapped in the mantle, but much of it eventually comes back up. It's released from the rock by intense heat, rises through magma, and erupts from volcanoes or mid-ocean ridges as steam. Over geological time, this cycle becomes a planetary heartbeat. Water in, water out. It's not fast, it's not dramatic, but it's steady, and it's vital. It's this internal breathing of the Earth that may have allowed the oceans to reach a stable volume. Without it, water might have just kept accumulating on the surface, or it might have vanished altogether. But with it, the oceans became a sustainable feature, a layer, not a flood. Still, there was another trigger, a slow-burning fuse that would eventually transform the oceans from simple chemical basins into biological incubators. And that trigger was oxygen. Not the oxygen we breathe today, not yet. But its slow, subtle introduction was inextricably linked to life itself. Around 3.8 billion years ago, as the earliest oceans settled into a rhythm, something extraordinary began to happen. The first signs of life appeared. These were microbes, simple, ancient, and utterly astonishing. They didn't need oxygen to survive. In fact, for most of them, it would have been toxic. Instead, they thrived on raw chemistry, using heat from hydrothermal vents or sunlight that filtered through the hazy sky to power their primitive metabolisms. Among these early life forms were cyanobacteria, tiny architects of planetary change. They often lived in shallow waters, clustering together in layered mats or domes that we now call stromatolites. And they did something that no creature had ever done before. They performed photosynthesis. They learned to use sunlight to convert carbon dioxide and water into energy, and in the process, they released oxygen as a byproduct. At first, that oxygen didn't linger in the atmosphere. As soon as it was produced, it bonded with all the dissolved iron in the oceans, forming rust-colored particles that sank and settled onto the seafloor. Over millions of years, these particles created distinct layers of rock that we can still find today. Banded iron formations, geological evidence of Earth's slow, gradual oxidation. But eventually, the iron in the oceans was all used up. The oxygen then began to accumulate, first saturating the oceans and then, finally, leaking out into the air. This marked the beginning of what scientists call the Great Oxidation Event, around 2.4 billion years ago. It wasn't fast, and it wasn't uniform, but it fundamentally reshaped the planet's chemistry, and the water along with it. The oceans became less acidic. New types of minerals began to form. Biological complexity exploded. Life had to adapt. Some organisms perished in this newly toxic world, but others evolved, and the atmosphere began its slow transformation toward the breathable blend we know today. All of this hinged on water. Water carried the carbon. Water housed the microbes. Water stabilized the climate, buffered the temperatures, and enabled chemical reactions that would have been impossible in a dry world. The planet's sculptor and thermostat. Yet, water was not just a passive medium for life. It actively shaped the very skin of the Earth. Over vast stretches of time, it carved valleys, wore down mountains, and created the fine sediments that would one day become soil. It formed rivers that rearranged the land. It became massive glaciers that ground rock into dust and reshaped entire landscapes during ice ages. But even more profoundly than that, water began to regulate the planet's thermostat. Thanks to its incredibly high heat capacity, water can absorb huge amounts of heat without its own temperature changing very much. This property helped Earth avoid the wild swings of climate that plague other planets. It allowed for moderation, for consistency, for long-term habitability. Beyond this, water enabled the formation of the carbonate-silicate cycle, a critical long-term feedback loop. It works like this. Carbon dioxide in the atmosphere dissolves in rainwater, making it slightly acidic. This acid rain falls on rocks, slowly weathering them down. This chemical reaction draws carbon dioxide out of the atmosphere and locks it into carbonate minerals, which are then washed into the ocean and eventually buried in sediments. This carbon is later returned to the atmosphere through volcanic activity. Without this grand, planet-spanning balance, Earth might have become a runaway greenhouse like Venus, or a frozen snowball like Mars. Instead, it stayed temperate, stable, and wet. It's worth taking a moment to consider Earth's unique hydrosphere compared to its rocky neighbors. Venus and Mars may have both had water once, possibly even oceans, but neither of them managed to hold on to it. Venus, being too close to the Sun, experienced a runaway greenhouse effect. Its oceans boiled off and were broken apart by intense solar radiation. The light hydrogen atoms escaped into space, the oxygen bonded with rock, and the planet was left bone dry under a crushing, toxic atmosphere of carbon dioxide. Mars, smaller and farther out, lost its internal heat more quickly. Its core cooled, its magnetic field faded, and without that protective shield, the solar wind stripped away most of its atmosphere. Any water that remained either froze at the poles and underground, or was lost to space. The rivers dried up. The seas vanished. Only Earth held on. It held on because of its size, its protective magnetic field, its perfect distance from the Sun, its deep internal cycles, and yes, a bit of luck. It was in many ways a perfect storm. And water was both the cause and the effect of that perfection. From stardust to storm clouds, from minerals to monsoons, water's journey wasn't just about delivery. It was about transformation, a shaping, a laying of a foundation, and that process is still ongoing today. Every single drop in your glass contains atoms older than the Earth itself. Hydrogen forged in the Big Bang, oxygen born in the hearts of dying stars. These elements came together not just once, but over and over again in the dark of space, in the heart of stone, and in the depths of the sea. And here they are, on your tongue, in your blood, in the tears we shed, and in the rain that feeds the forests. The water we know is ancient, restless, and utterly irreplaceable. And as we trace its origins, we see not just how water came to Earth, but how, through water, Earth truly became itself. When Earth's surface finally cooled enough to cradle oceans, the presence of water didn't simply mark a new phase in the planet's evolution. It rewrote the rules of what a planet could be. This wasn't just the appearance of a new chemical. It was the onset of a cascade. Water, so seemingly simple, became a catalyst for change so sweeping that it touched every part of the Earth, from the crust below to the skies above. It didn't just fill basins. It began to sculpt continents, regulate the climate, and alter the planet's chemistry in irreversible ways. To begin, we have to return to the crust Earth's thin surface shell, fractured and floating on the hot, pliable mantle below. With the arrival of vast amounts of water, this crust underwent a subtle but profound weakening. Here's why that matters. Water acts like a lubricant in geological systems. It lowers the melting point of rocks. It infiltrates faults. It slips between mineral grains and makes them more mobile. When dragged down into the mantle during subduction, it causes the surrounding rock to melt more readily, fueling the volcanism that builds island arcs and new continental crust. In short, water made plate tectonics possible. Not just the system of moving plates we know today, but the very capacity for the Earth's surface to shift, recycle, and renew itself. Without water, Earth's outer layer might have remained rigid and static, like the surfaces of Mercury or the Moon. Instead, it cracked into mobile plates. These plates began to move, colliding, pulling apart, and sliding past one another, creating mountain ranges, deep ocean trenches, and volcanic chains. This constant movement gave the Earth its dynamic geology, and it continues to this day. Earthquakes, volcanoes, the rifting of continents, all of these owe something to water's subtle influence, deep below our feet, a chain reaction of change. But the consequences didn't end with the crust. As the oceans deepened, they became vast chemical laboratories. Rainwater, made slightly acidic by dissolved gases, began to erode the first land masses. This process, called weathering, broke down rock into sediments and released a flood of minerals into the sea. This runoff fed the oceans with calcium, magnesium, sodium, and potassium, the very elemental flavors that still define seawater today. Over millions of years, these reactions also drew carbon dioxide out of the atmosphere, locking it away in carbonate rocks on the seafloor and cooling the planet in the process. This was the beginning of Earth's long-term carbon cycle, a planetary thermostat written and regulated by water. At the same time, the seas grew rich in dissolved iron, a consequence of the lack of free oxygen. This set the stage for one of Earth's most dramatic transformations, the oxygenation of the atmosphere. We've touched on this before, the quiet work of cyanobacteria and their photosynthetic ways. But this is where the chain reaction truly begins. Cyanobacteria, living in the shallow edges of the ancient oceans, began producing oxygen. At first, this oxygen didn't accumulate in the air. It immediately reacted with all that iron in the water, forming iron oxide rust, which then sank and layered onto the seafloor. These deposits would become the banded iron formations that geologists now mine and study. Only after the iron in the oceans was completely saturated did oxygen finally begin to build up in the water and, eventually, in the atmosphere. This slow rise of oxygen, the Great Oxidation Event, transformed the entire biosphere. Oxygen is highly reactive. It breaks bonds, it fuels combustion and metabolism. When it first appeared in significant amounts, it was toxic to most of the life that existed at the time. Entire microbial communities were wiped out in an extinction by oxidation. But for others, for the organisms that could adapt or evolve to use it, oxygen offered something new: energy. Vast amounts of it. Aerobic respiration, which uses oxygen to unlock energy from food, is far more efficient than anaerobic methods. It allowed life to become more complex, more active, more ambitious. And this too was a water-driven change. Without oceans, there would have been no place for cyanobacteria to thrive. Without water, there would have been no medium for the oxygen to dissolve, spread, and react. Water created the stage, and life took its cue. Meanwhile, back at the surface, water continued its quiet work, cracking rocks, smoothing landscapes, and moving sediments. Glaciers formed in the colder latitudes and at high elevations, carving out U-shaped valleys and grinding mountains into fine silt. Rivers wove their way through the land like silver veins, creating deltas and floodplains rich in nutrients. The hydrological cycle, the endless loop of evaporation, condensation, and precipitation powered by the sun, became one of Earth's dominant engines. It redistributed heat, shaped climate zones, and delivered fresh water to the continents. And with this came something else: true habitability. Not just in the sense of survivable conditions, but in the profound sense that complex ecosystems could take root, spread, and diversify. Tidal pools, riverbanks, wetlands, each became a crucible for life to experiment with new forms and new strategies. Water enabled evolution to flourish. This endless, cycling partnership between water and rock, water and air, and water and life defines our planet. It is not a simple chain of events. It is a spiral, a self-sustaining dance, and water is the rhythm that drives it all. Look around you now. The sky outside might be overcast or a brilliant blue. The ground may be soaked from a recent shower, frozen, or dry as dust. But somewhere above you, beneath you, within you, water is moving. Quietly, relentlessly, a mist, a trickle, a pulse. Earth is breathing, and that breath is wet. And we, you, me, all of us are part of that movement. We often forget that. We talk about water as if it's out there, as if it's a commodity to be managed or extracted. But in truth, it is a mirror. When we study water's incredible journey from the stars to our world, we are studying our own. Because every single drop of water on this planet, ancient, restless, and nearly immortal, tells the story not just of planetary formation, but of what it means to be alive, right here, right now, in this fragile moment. It's strange to think how recently we've come to understand water's true role. Just a few centuries ago, we thought water was one of the classical elements, unchanging and indivisible. We didn't know it had a molecular structure. We certainly didn't know it held a memory, not in a mystical sense, but in a scientific one, the kind that lingers in isotopes and sediments, in glacial ice layers and ancient salt flats. Today, we can map underground aquifers with satellites. We can sample the tails of comets with robotic spacecraft. We can watch a single droplet form in slow motion and see the physics of surface tension unfolding like a delicate dance. And still, for all our incredible tools and models, water remains elusive in its full implications. Because the story of water is not just geological or chemical, it's becoming a moral one. We live in a time when climate change is no longer a distant theory. The ice is melting, the seas are rising, droughts are deepening, floods are growing fiercer, rivers are running dry while entire cities are growing thirsty. Water, which for so long has been our inheritance, is now becoming our shared responsibility. The very planetary cycles that made Earth habitable, the ones that buffered its climate, cycled its carbon, and regulated its temperature, are now being strained by our own actions. And yet, even here, there is a kind of hope. Because just as water created the conditions for life to begin, so too can it inspire a kind of humility in us. A river teaches patience. An aquifer teaches foresight. A glacier teaches endurance. And when we protect water, when we restore wetlands, repair watersheds, and reduce pollution, we are not just preserving a resource. We are participating in a story that began long before us and will, if we are wise, continue long after we are gone. That story stretches from stardust to sustainability. It links the hydrogen in your blood to the hydrogen in a comet's tail. It connects the oxygen you breathe to the oxygen once released by ancient algae, drifting in shallow primordial seas. It reminds us that we are not separate from Earth's systems. We are systems within systems. Water within water. Consciousness within chemistry. And if Earth's long past has taught us anything, it's that resilience is real, but it is not inevitable. The planet has recovered from asteroid impacts, from supervolcanoes, and from mass extinctions. Life has clawed its way back from the brink again and again. But that recovery takes time, millions of years, entire epochs. We don't have that kind of time, so here we are, at the shoreline of a story older than mountains and deeper than time. We've followed water from the cold edges of space to the hot belly of the Earth. We've watched it fall, rise, reshape, and return. We've seen it cradle life, challenge it, and carry it through fire and ice. And we've glimpsed how it still flows, quietly holding together the pieces of this fragile, magnificent planet. Maybe now we can ask the question a little differently. Not just, where did the water come from? But what does it mean to belong to a world made of water? To know that your heartbeat, your breath, your very thoughts are all stirred and sustained by the same ancient current that wore down continents and lifted whales. To realize that the cup in your hand contains the echoes of comets, of clouds, of crocodiles, and of poets. That nothing you touch, no fruit, no book, no bird exists without water's quiet signature. And that, in turn, you are part of that cycle. Not a bystander, not an observer, but a participant. So take care of the rain. Walk gently by the stream. Let your oar be active. Because wonder isn't just a feeling, it's a decision. A way of seeing, again and again, the miracle in the mundane. Thank you for joining me on this journey through Earth's most enduring element. If this story stirred something in you, a question, a memory, a ripple of wonder, feel free to share it in the comments below. I'd love to know what water means to you. And if you'd like to hear more stories like this one, slow, deep and full of quiet science, please feel free to like, subscribe and settle in with us next time. We've only just begun to trace the threads of Earth's ancient saga. Until then, stay curious, stay kind and stay fluid. This has been Just About Earth, and I'll see you again downstream.